Welcome everyone. Today we are diving into XFlow, a groundbreaking system designed for governing agentic uncertainty. We are moving beyond simple prompt chaining to introduce an executable protocol programming system that builds highly reliable multi-agent workflows through semi-formal architectural constraints. Let's explore how it works. To understand why XFlow is necessary, we first need to identify the core flaw in our current multi-agent foundations, the underspecified boundary. In traditional setups, tentative agent thoughts, like an AI thinking "I think this task is maybe done," are accidentally reused as committed facts, mutating data downstream. This inevitably leads to silent, dangerous error propagation. If we look at the orchestration spectrum, we have two extremes today. On the left, we have rigid markup systems like YAML or DAGs. They are fully checkable but lack semantic state. Adapting to new evidence requires rewriting the whole graph rather than just a state transition. On the right, we have prompt-only agents like LangChain or AutoGen, which offer open reasoning but rely on implicit state, leading to those silent errors. XFlow and its protocol format, XPF, represent the ideal semi-formal solution in the middle. By using typed states as gates for informal soft outputs, the system becomes both structured and highly expressive. Welcome to the executable protocol programming paradigm. XFlow achieves reliability by creating an explicit boundary. On one side, you have informal semantic information, context, intent, rationale, and open reasoning. On the other side, you have formal structural information, strict states, actions, schemas, and transitions. XPF keeps the informal, semantic work strictly locked inside the actors, while moving workflow commitments into a structural harness where they can be mechanically checked and enforced. Let's look at the anatomy of an XPF protocol in action. It is built on a few key pillars. First, symbols, which represent our shared typed state. Second, interfaces, which define strict actor boundaries. Third, derivations, which handle computed dependencies. Fourth, flow, which dictates checked transitions. And finally, handoffs, which manage the safe transfer of responsibility. How exactly do we govern uncertainty with these symbols? In XFlow, a symbol is not just a variable injected into a prompt, it is a typed runtime state cell. Before informal actor outputs can influence downstream decisions, they must pass through a strict lifecycle mediation. They start as proposed input, go through a schema check to become validated, and finally pass a policy check to be officially committed. Think of the AI actor as a typed function. XFlow does not attempt to constrain the LLM's internal semantic reasoning, that remains a black box. Instead, it wraps the entire invocation in a typed boundary. Prompts are constructed exclusively from declared input symbols, and the model's responses must map exactly to declared output schemas. Furthermore, XFlow introduces reactive state invalidation, inspired by functional reactive programming. When a committed value is modified by an actor or user, the system detects this via derivations, automatically marks any dependent downstream symbols as stale, and halts or schedules recomputation. Actors no longer need to magically remember to reevaluate downstream logic. The system architecture flows seamlessly from text to runtime. You begin with a specification detailing your protocol, stages, and flow rules. This is then compiled, parsed, resolved, and type-checked into a typed intermediate representation before any actor even runs. In XFlow, what you say is exactly what you execute, statically checked for broken references before execution. To synthesize our core insight, generative AI is inherently informal, and XFlow does not attempt to structure the LLM's brain. Instead, reliability is achieved by building an inescapable, formal airlock, a schema, policy, and lifecycle gate around the model. This boundary dictates exactly how AI thoughts become system actions. Let's diagnose some common agent failure modes. For premature mutations, like executing a tool based on a prompt assumption, XFlow uses a handoff gate that requires explicit human confirmation before execution. To combat silent hallucinations in business logic, it uses derived verification symbols that apply deterministic logic mechanically outside the prompt. And for context bleed, where an agent edits the wrong file, interface bounds restrict actor visibility strictly to assigned input symbols. Let's look at some proofs, starting with constrained interaction. In a standard React baseline, an LLM might instantly trigger a mutating tool call without asking, violating policy. XFlow, however, uses explicit constraints to block the unauthorized tool call, forcing a required confirmation symbol. The LLM must ask the user for permission, ensuring 100% compliance before the tool executes. Proof 2. Long context reasoning. When relying on prompt-based reasoning, LLMs often hallucinate logic when performing math or interpreting business rules. XFlow shifts this burden to deterministic derivations. The LLM simply extracts raw values, and XFlow mechanically calculates the math and applies the business rules outside the prompt, ensuring accuracy. Proof 3 looks at agentic software engineering. A baseline agent might submit a code patch, ignore failing local tests, and force a bad commit anyway. XFlow fixes this with gated execution. Software engineering norms cannot just be prompted, they must be gated. XFlow mechanically prevents commits until local validation symbols return true, forcing the agent to retry its work. XFlow also acts as a critical infrastructure layer in cloud-edge multi-agent architectures. Imagine a massive cloud orchestrator acting as a global planner. XFlow serves as an executable firewall, using scoped inputs, I/O schemas, and coverage thresholds between this global cloud planner and a pool of smaller, strictly confined local workers on the edge. For open-ended tasks like deep research, XFlow completely protocolizes the workflow. While cloud orchestration handles high-level semantic decisions, XFlow gates enforce hard coverage checks and confidence thresholds. Vague instructions like conduct sufficient research are replaced by hard-derived metrics, and edge workers are restricted to narrow, verifiable actions, like a web searcher that cannot modify the core query, or a fact extractor that cannot add unmentioned information. Ultimately, the boundary is the solution. Reliability in AI systems does not come from trying to eliminate uncertainty or structuring the LLM's internal reasoning. True reliability comes from designing an explicit, enforceable boundary between the actor and the system state. XFlow provides the exact language and runtime needed to build that boundary. Thank you for watching.